Hey everybody, and welcome to chapter 13. This chapter we are talking about problem solving and intelligence. Now the book does have a few pages about creativity. We're actually not going to cover that stuff this semester. I found that stuff in the textbook to be pretty unsatisfying and not super interesting or informative or even representative of what you would find on that topic in cognitive psychology, so I'm just not going to cover it. It's not going to be on the test or anything like that. This video might be a little bit on the long side just because we have a lot to cover. What we're mostly going to be focusing on is going to be looking at how we try to approach problem solving. So what kinds of things do we do in order to try to solve problems and achieve our goals? The next couple of videos then are going to be about how those problems are represented, and then finally what intelligence looks like in the cognitive psychology literature. All right, so whenever I talk about problem solving, luckily, this is something that I feel like is super straightforward. What is problem solving? Is basically solving problems, right? But really what we're talking about is trying to achieve a certain kind of goal, which makes this very, very ambiguous or abstract, because that could be almost anything, right? Like me going and making food, that is achieving a goal. That is problem solving. Me trying to solve a riddle or jigsaw puzzle, these types of things that we normally think of as problem solving, that is also problem solving. So anything where you can kind of choose from a list of behaviors how you approach achieving your goal is going to be an example of problem solving. Another example of problem solving is making a good grade in your cognitive psychology class. That is something that you have to choose these different strategies. You have to try to achieve that goal. All right, so let's get into it. When we talk about problem solving, this chapter is almost exclusively towards humans. It's almost all about human problem solving, which, as you know me by now, I'm a little bit unsatisfied with that. I think that there's a lot of really interesting examples of problem solving in non-human animals. Here are 3 videos. I think those links still work. I tested them recently, but they are fascinating examples of problem solving for non-human animals. You're going to see this with pigeons, with crows, with chimpanzees and monkeys. You're going to find it in squids and dolphins and octopi, in worms. You'll find examples of goal achieving, however you want to define that, different. Across the animal kingdom. So we all engage in problem solving, and for a lot of what we're going to be talking about in this section is also going to apply to non-humans as well. We're just pretty much all going to give human examples though. So when we talk about problem solving, there are 3 different kinds of components that we want to talk about, that we want to kind of use to describe what problem solving is. The first, as I mentioned, is trying to achieve a goal. So you have this goal directedness where your behavior is targeted towards trying to achieve something, trying to find or realize this specific outcome. The second piece is going to be sub-goal decomposition, which is a really fancy way of saying that now that you know what the goal is, you're going to try to divide your behaviors up so that you have separate stages to achieve in order to get that goal. If we're talking about making a good grade in this class, an example of that would be striving to do well on every exam. Because that is a sub-goal that you can work towards to help you realize that final goal, which is achieving a good grade. And then finally, you have operator application, which sounds very scientific, right? But really all that means is the ability for you to kind of choose amongst different kinds of behaviors. If I gave you a goal to do, and only gave you one specific tool and one specific strategy, and I said this is all you can use, you have to follow these instructions, that is not problem solving, right? That's just following instructions. That's just doing a behavior. So you have to be able to have the variety of behaviors to choose from in order to solve that problem, in order for it to technically be problem solving. All right, so we're going to talk about two big words that are going to come up a lot are going to be operators and states. So states, well actually let's start with operators. Operators are, like we mentioned in the previous slide, any kind of behavior in which you are using to try to solve a problem. That's what an operator is. So any kind of technique, any kind of behavior you do, whether it be hands-on or mental calculations or whatever, those are all operators. States, on the other hand, are going to be different parts of the problem. So basically kind of like different time points almost. Yeah, I think that's a fine way to put it. Basically, we're going to have a couple of different, or a few different kinds of states. We're going to have the start state, which is basically right when you begin the problem. That's where things are. That's the start state. The goal state then is going to be whatever the solution is. So whatever it is, whatever it takes to solve this or to do it completely is going to be the solution. So again, if we're applying this to doing well in cognitive psychology, the very beginning of the semester is going to be your start state, and then the goal state is essentially going to be whenever you do your very last assignment, because that will be what depends on your grade in the class. And then everything up between that, between the start state and the goal state, is going to be called the intermediate state, and we're going to call specifically the state that we are on right now the current state. So right now we are all in the current state, right? But we're also in an intermediate state. We're not at the beginning, we're not at the end, we're just somewhere in the middle. So we're finding these different situations that are after the problem has already started, but before it has technically been solved. All right, so let's talk, and this is what the most of this video is going to be about, is going to be how we pick the right operator. So how we pick the right strategy in order to solve a specific problem. There are 3 different ones that we're going to talk about that are explained in the book, and these 3 are, I think, best illustrated whenever I give you an example or a riddle. So if you've already read ahead in the textbook, you've seen a puzzle very similar to this, so you may already know how to solve it, or if you've heard it before, you probably know how as well, but here we go, let's try it out. So I want you to play along. This is the chicken, grain, and wolf problem. So in this problem, basically, you are at a river, and you have 3 things with you. You have a chicken, a bag of grain, and a wolf, and it is your job to cross that river, taking those 3 things with you. The problem then is that you only have 1 canoe, and in that canoe you can only take 1 thing with you at a time. So the rules here are that you can't leave the chicken with the grain because the chicken is going to eat the grain, and you can't leave the wolf with the chicken because the wolf will eat the chicken. So how do you get everything over from one side of the river to the other in this canoe that can only take 1 thing at a time without leaving the chicken and the grain together or the wolf and the chicken together? So I encourage you to pause this video, try to solve this on your own, and then check back in whenever you think you have a solution or whenever you feel like you give up. Alright, so whenever I do this in the classroom, it's a lot of fun because people will try to kind of move things over. They try to, to answer it. And then whenever I go through how it is actually answered, people feel like it's cheating. They feel like it's not fair. So here's how you would do it. First, you want to take the chicken over, because if you do that, you're going to leave the wolf and the grain behind by themselves. That's okay, that's safe. And then you're going to leave the chicken over at the other side. So far, so good. Most people do that first, too. Then we're going to go back across the river, and then we're going to grab the wolf. We're going to take that wolf, and we're going to bring it to the other side of the river. But here's where things are a little different. We're no longer going to leave the chicken on that side of the river. We're actually going to bring it back to the first side of the river with us, so that it's just the wolf that's left over there. So we do that, and then once we get back, then we grab the grain, and then we go to the other side, we leave the grain with the wolf, and then we go back, and then we get the chicken, and then we bring the chicken, and then we have all 3 things at the other side of the river. So when I go through that example, first off, a lot of people have trouble with this puzzle when I first lay it out. And second, whenever I go through the solution, people feel a little bit like I've cheated. So let's talk about those 2 different things. Why is this hard? Why does it feel unfair? So the first piece that I want to talk about is called backup avoidance. And backup avoidance is our natural tendency to move from our current state towards the goal state. We want to basically keep moving forward. We don't like the idea that we are moving backwards. So whenever we're doing backup avoidance, we want to continue moving forward and trying to continually finding ways to get us closer and closer and closer to that goal state. In that case, it's having those 3 things on the side of the river. So why is the chicken, the grain, and the wolf riddle so tricky? It's because we don't want to revert back to a previous state. We don't want to go back where now we have, instead of 2 things on the island, we take that wolf over there. Now we don't want to bring back and have two things on the first side of the island again, because now we just have one thing over there, right? So we don't want to back up, we don't want to go backwards, and because of that, that makes it kind of tricky. Now, like we talked about with the decision-making chapter, all of the things that we're going to be talking about as like different kinds of ways that we pick strategies and pick different behaviors to solve these problems, these are all good things. It's just that in examples like this is whenever we really see when they fail us and when they let us down. But normally backup avoidance is a very good way of solving problems. In this case, though, it doesn't work, and because it doesn't work, it highlights how much we like doing backup avoidance and how strong a connection we feel with continuing to do it. All right, so bringing the chicken back to the beginning then feels like a step back. It feels like we are moving to a previous state, and we don't like that. Very similar to that, we have something called difference reduction. And difference reduction is whenever we try to choose different strategies that are going to reduce the difference between your current state and the goal state. So we're going to try to pick different kinds of strategies, different kinds of behaviors that are going to take where we are right now to get us closer to the goal state. In this case, to having those three things over on the right side of the island, or in terms of grades, to reduce where we are now in terms of grades to having a good grade in the class. We want to try to remove those differences in order to get there. So again, we can look at the chicken, grain, and wolf example to illustrate how this works for us, or in which cases it goes wrong for us. That basically, once we have the chicken on the other side of the river, it actually feels like we are expanding the difference between our current state and the goal state to take that chicken back on the other side. So not only does it feel like we're going backwards, but now it feels like the current state now looks even less like the goal state that we want to be in. So because of that, it feels like we're increasing the difference between those two states. And then finally, we have means-ends analysis. And in means-ends analysis, essentially what we are doing is we are going to use those previous operators, those previous different things, but now we are going to create sub-goals that are going to help us take out the differences between where we are right now and where we need to be. So you can think of it like this. Instead of doing all of these things, trying to get to the final stage, trying to get to that final goal state. Instead, what we want to do is we want to create little goals for ourselves. So we're thinking about this in terms of the chicken, the grain, and the wolf. Then our goal is no longer to bring them all to one side. Our goal is going to be, how do we get two things on the same side without fighting, without eating one another? And if that's your sub-goal, then it's much easier to approach this problem. It's just that most of us don't take time to stop and think about what that sub-goal should be. In terms of thinking about how can we apply this to making a good grade in our class, maybe it's that you have set out this goal that, okay, I want to make all A's on the quizzes, or I want to make all A's on the exams. That is an example of means-ends analysis. You're identifying some smaller goals that will help you achieve the larger goal. So this is different than the other reasons, and it's particularly because what we're doing is we're creating this sub-goal, and we're going to choose behavior specifically for achieving that sub-goal that will get us there. And if we find that there's a behavior that doesn't work, we're going to set it aside, and we're going to try again later when we're at a different state. All right, so how do we choose these strategies that help us solve a problem? Basically, here's this nifty little graph that shows you difference reduction, but I feel like maybe the best way to illustrate this, in the next slide I'll illustrate it in just a second, but basically what we're trying to do here is we're trying to get from our current state to the goal state. And so let's say that we're starting out, we are trying to eliminate the difference between these states, and if we can't do it, then we've failed, and then we give up. But if we do win it right, then we move over and we get to this point and we check to see whether or not we've made any progress, and if we don't need to make any more progress, then we have a success. If we feel like there are still some differences, then we need to find new behaviors in order to try to get further and further and further along. So an example of why means-ends analysis is important is because in this case, you see this doggy, he's trying to get to his bone, right? He's trying to get to this dish over here. And so he's pushed up against this fence. He's not able to really get any closer. here, right? And so his best option is obviously going to be to move around, to come around. But if he does that, he's going to be increasing the distance away from that particular bowl. Now we know that that's a good thing, right? But this dog in this drawing doesn't know that. And so he's practicing difference reduction. He's just trying to reduce the difference between where he is and where he needs to be. What means-ends analysis would say is like, okay, well, we've tried this and it doesn't work. So let's create a sub-goal. Let's try to create some sub-goal that we can. In this case, let's say that maybe the sub-goal is to get on the other side of the fence. So now we're not exactly trying to get this bowl. We're just going to try to get on the other side of the fence. And so then all he would need to do is walk around. And so he's now reducing the difference between his state over here, his current state here, and the goal state. And then once that difference is eliminated, then he's able to go to this next goal, which is going to be to get to the food. And that's what this flow chart right here illustrates. Basically, the only difference here is that we've added in this component right here that we're going to, this one right here, that we're going to be basically kind of trying to reduce the difference. And if we can't do that, then we're going to try to create a sub goal so that we can reduce the difference between that to get us closer to our ultimate goal state. All right, so here is an example of another example of of operator selection. So here we have this is an old riddle or old puzzle. So your goal is to essentially get these 5 discs that are on this peg and to move them all in this order over to C, to the C peg. So how do you do that? And actually, I forgot to mention that the big rule here that's hard is that you're not allowed to have a larger disc on top of a smaller disc. Only smaller discs can go on larger discs. Larger discs cannot go on smaller discs. All right, so how would you do this? I'll let you pause it and I'll let you try to figure it out mentally, and then I'll check back in with you. All right, so if you took time to try this out, I remember when I first tried it out, I thought I was getting along well, and then I got stuck. But again, think about applying sub-goals. If you weren't able to solve it first, try to think about how you could achieve the sub-goal. The sub-goal, obviously, that we want to try is like, okay, we want to try to not get all of this over there. That can come later. We want to try to get this largest disc right here. We want to get that over here. That's going to be our first goal. And if you approach it that way, I think you'll find that this is solvable, that it is somewhat manageable. It's hard, it's tricky sometimes, but manageable. So here's an I hit the wrong button. So here's an example of the Tower of Hanoi solved, I guess. You can see here. All right, so it takes some time, right? And you have to go a little bit contrary to what you would have guessed, right? Or what you may have initially felt. Remember that the reason why we're talking about this is to illustrate things like backup avoidance and difference reduction. That once we get to this point right here, we don't want to go back. We don't want to have to send things back over to the starting peg, right? Because we've identified this is the start state over here. We want to get everything to the goal state. We don't like the idea of moving things back over here because it feels like we're getting farther away from where we need to be. Now, the fascinating thing about the Tower of Hanoi not only is that it's tricky, but also that other researchers have used this as a way to study problem solving. And these researchers right here, they did this really cool study where basically they had people kind of do it on their own, and then another group, they gave them this hint. We want you to create sub-goals. We want your first goal to be to get this large disc over to this other peg. And essentially what happened is that whenever people engaged in just a difference reduction task, they found the task to be unsolvable and unmanageable, and they couldn't do it. But whenever people were using means-ends analysis, they were able to solve it, and they were able to complete it just by imagining these sub-goals that we would need to achieve in order to achieve this larger goal. All right, that's where I'm going to end it for now. I'm going to check back in with you in the next video here, talking about problem representation. Bye.